So, as the sun sets over Granite Mountain, let's finally have a look then at how we reduce our aircraft equations of motion for a perturbed flight condition. So, as we summarized at the start of this little section, this is for an aircraft during a maneuver or as a result of turbulence, for example, and this describes how an aircraft deviates from its steady state condition or trim condition. Sorry about the squeaky chair. So, what we do is we separate our variables up here and give our steady state condition these subscript 1s, and then we apply a small perturbation to that steady state condition given by the lowercase, either lowercase of the capital letters or lowercase Greek letters, right? So we have here as an example of the x component of the linear velocity as given by the steady state condition plus a small perturbation, and that's the same for all of our linear and angular velocity components. We do the same for our Euler angles and the same for our aerodynamic and thrust forces and moments. So you can see where this is going. We now have to make these substitutions, so replacing all of these variables in our conservation of linear momentum equations and conservation of angular momentum equations with these substitutions, the steady state variable plus the small perturbation. And as you can probably imagine, that turns into a huge mess. So all I've done here is written out the conservation of linear momentum equations and conservation angular momentum equations with those small perturbations applied to the steady state condition for all of our variables. Now, in order to reduce this huge mess, we can make two assumptions. The first assumption that we make is that the product of two of these small perturbations in linear or angular velocity, so if we look at how we describe these, so if we have a lowercase u multiplied by a lowercase v, for example, then we're just going to assume that is negligibly small and we're going to just equate it to 0. The next thing we can do is a similar thing for the Euler angles. So we assume that the product of two of these small perturbations in Euler angle is also negligibly small, and we're going to equate those to 0 in order to reduce this thing. And two other things to consider here. We're going to assume the small angle approximation for sine. So that basically means that if we have the sine of a small thing, so this is sine of a small perturbation in psi, we're going to assume that's just psi, and the same for theta and phi. So the only thing to remember with this small angle approximation is that the sine of a small thing is equal to the small thing but in radians, right? And also the small angle approximation for cosine says that the cosine of a small thing is approximately 1. So those are the assumptions that we're gonna use in order to reduce this crazy mess. And these approximations are good up to angles of approximately 16 to 18 degrees. So that takes us up to, that includes basically all of our normal flight regimes, let's say. So the first thing we're going to do, considering these approximations, is just consider these trigonometric parts here on the right hand side of the conservation of linear momentum equations. So you can see here I've used a trigonometric identity to expand this thing out, and then I've used the approximations, right? So we said the cosine of a small thing is approximately 1 and the sine of a small thing is approximately the small thing but in radians. So I'm able to use this trigonometric identity to expand out those and simplify it down using the approximations that we've just made. So I do that over and over again for the different trigonometric identities that we have on the right hand side of these equations up here, and we expand them out first, simplify them down using our assumptions to get the following. So the other thing I've done here is I've included those trigonometric simplifications that we've just been through, but I've also gone ahead and expanded out these terms here on the left hand side. So that's what I've got here. Remember, we're also assuming that the product of two small perturbations is 0, so I've gone ahead and labelled all of those on as well. And I've done exactly the same thing for the conservation of angular momentum equations, namely multiplied out all of those terms on the left hand side, like in here. Now, the thing to realise about what I've written down here is that all of the terms that don't include a small perturbation, so all of these ones, those are essentially the equations which relate to the steady state condition. So we can take those out, right, because we're only interested in what happens with this small perturbation. So any terms which correspond directly to the steady state condition we can take out as well, and these are the ones that I've underlined in red. So that's going to further reduce down our system. So I've got rid of all of the stuff that's going to be 0, I've got rid of the steady state condition, and I'm left with this, which looks a lot neater and tidier. So these are the conservation of linear momentum equations and conservation of angular momentum equations for a perturbed flight condition. So the next thing we do is turn our attention to the kinematic equations. So you'll recall the kinematic equations are given by this matrix equation system here. So I've rewritten that out in component form, and then again what we do is we go ahead and apply a small perturbation to each of these Euler angles, and we get this system here. So I've just applied a small perturbation to each of those Euler angles and written it out in full. Again, we can reuse our trigonometric identities as we did for the conservation of linear momentum and angular momentum equations, using our assumptions again just following this all the way through, expanding out, then using our assumptions to reduce the system down in exactly the same way as we just did for the conservation of linear momentum equations and conservation of angular momentum equations. And finally, we may write down our kinematic equations. Now again, I've gone ahead and multiplied everything out, written it out in full so that I can see where my steady state kinematic equations are. So again, the variables or the terms in these equations which don't include a small perturbation, so again all of the ones I've underlined in red, correspond to the steady state kinematic equations and therefore can be removed from this system because we're only interested in the small perturbations. So again, if I remove all of those terms, use our approximations to get rid of some of the other terms, a lot of these go to 0, look, what we end up with here is finally the kinematic equations for a perturbed flight condition. So these, in conjunction with our conservation of linear momentum equation, conservation of angular momentum equations for the perturbed flight condition.